Swayam Prabha. Digital India. Educated India.
Hello everyone. Now today we'll start a new topic which is mechanical characteristics. The analytical approaches of measurement of mechanical characteristics that we will discuss in this module. The things which will be covered is mechanical, all the mechanical characteristics, like we'll cover the tensile behavior of textile material, which will be a major part. Apart from that, we will discuss the low stress mechanical characteristics of fabrics. So tensile behavior we will discuss for fiber, yarn as well as the fabric, but the low stress mechanical is applicable for fabric, that we will discuss, where the bending, shear, drape characteristics, everything will be covered in that segment. So first, the tensile testing. So if it is asked that what is the quality of a material, so if someone asks the simple term, what is the quality of the material for a fiber, yarn, if we test, the first thing which comes into our mind, the strength. So to know the level of strength provided by the material, it's basically that the strength which comes out for anything, it's called resistance. Suppose someone is pushing me, okay, and I will try to resist, okay, and depending on my strength, I will be able to resist. If the force applied on me is more than my inherent capability, that is inherent strength, then I will not be able to resist. Similarly, for any material, say yarn, when we apply the force, say longitudinal force when we apply, so inherent characteristics of the material is to resist the load. That is called the strength of the material. So for textile material, the strength is very important for industrial and technical products. For example, any technical textile like rope, here strength is very important. Like ballistic clothing. So strength, that may be tear, maybe impact type strength. But for apparel textile, although it's important, but the requirement is not that stringent. So basically the strength is important for every material, but the for industrial and technical textiles, it's very important. For household and apparel, we merely need an adequate strength to withstand the force applied during daily activity. For clothing, apparel clothing, we need yarn strength just to withstand the handling during production and use. So let us see what are the factors which affect the strength of textile. So starting with the fiber, the molecular structure of the polymer controls the strength of the material, or we can say it's a load elongation behavior of the material. If the molecular structure is, the fiber molecular orientation is parallel to the axis of the fiber, then we will get higher modulus. Similarly, with the molecular orientation which is not oriented, in that case we will get lower strength or lower modulus. Number and intensity of the weak places. So strength of a material is nothing but the strength of its weakest point. Suppose we have two yarns of same mean strength x bar, same mean strength, and yarn 1 is having the strength variability. This is in y axis, its strength. Okay, so along the length, the strength is like this, and on other case, another yarn with the variability in strength is high. So we can see in the yarn 2, the number of weak points are more. Although both the yarns are of having same mean strength, but due to the higher number of weak points in yarn 2, so effective strength of this yarn will be low. So because the yarn breaks at its weakest point. As far as the staple yarn is concerned, we have discussed while discussing the fiber fineness, for same yarn linear density, if we use the finer fiber if we use, like this is the yarn 1 and yarn cross section of yarn 2, both the yarns are of same linear density, but yarn 1 is made of finer fiber and yarn 2 is made of coarser fiber. As finer fiber has got higher specific surface area, so fiber to fiber contact area will be more, there will be higher cohesion and will result higher strength with equivalent cross sectional area. Now, relative humidity and temperature. So, relative humidity also plays a major role. Most of the fibers, after absorbing moisture, reduces the strength. So, strength drops with the increase in moisture content, except only for cotton. Okay, and temperature also plays a role. If the temperature is very high, it's above the say melting point, or above, not even melting point, the softening point, then the strength will drop drastically. Okay. And also at, if the temperature is very low, sub-zero temperature, sometimes the polymer, the brittleness increases, so tensile characteristics will be different. Elasticity is another factor. So the strength is that when an external force is applied to any material, it is balanced by the internal resistance developed in the molecular structure of the material. So the internal force developed in the molecular structure will try to resist the external force. Now, tensile force is measured for textile material in the fiber, yarn, and also in fabric. In fiber, we measure the tensile strength in two forms. One is in bundle form. So, number of fibers are taken together, particularly for cotton, where variability is very high. For natural fiber, most of the natural fibers, like cotton, wool also, if the variability is high, then it's better to test the bundle strength to get the average value. But the man-made fibers are usually tested in individual form. as there is very less variation in length and fineness of fibre. So, cotton is tested in bundle form and man-made fiber is tested in the single fiber due to high variation in terms of length and fineness. So, what it is done here? A bunch of fiber is taken. First bundle is prepared, a bunch of fiber is taken, okay, and this is called a bundle. And then, so this is a fiber bundle. You prepare the fiber bundle, then the bundle is gripped by two jaws. This is jaw 1, left jaw, and another jaw is and they are pulled apart to measure the strength of the bundle. So the jaws are moved until the fiber break and we measure the strength. So breaking load and elongation at break are noted. So tensile strength or tenacity, can say tensile strength or tenacity of fiber bundle in gram per text is expressed in terms of the breaking load in kg. So when we measure the load, the breaking load in kg, it's measured. Length of the specimen, that means when we are testing, we are preparing the bundle. First we prepare the bundle. The system is that we prepare the bundle, then it is placed in the jaw, inside the jaw, and whatever fibers are projected, these projected fibers are cut and separated. Okay, and finally the jaws will be like this is the left jaw, and here we start the next jaw is started with in when it's they are in touch with each other. So the left jaw, this is the left jaw and right jaw. Two jaws are there, and fibers are, after cutting, the fiber bundles are within this. So length of the sample is the summation of the width of the left jaw and right jaw, and typically in bundle strength testing for cotton, it has observed it's typically around 11.8 millimeter. That we will discuss. because bundle strength testing is done by either stelometer or by Presley tester. So in both the cases, the bundle's length is typically around 11.8 millimeter, which is fixed. But here one can see as the jaws are touching each other. This is the bundle, and this is right jaw and left jaw. They are touching each other. That's why this condition is known as the zero gauge length. What is the gauge length? Gauge length is the distance between two jaws during tensile testing. So for zero gauge length, gauge test, the length of the fiber is 11.8 millimeter. And another way to test for 3 millimeter gauge. In that case, there will be gap between left and right jaw, and in that case, the total length of the fiber bundle, length of the sample in millimeter will be 11.8 plus 3, so 14.8 millimeter length, and this is fixed for the instrument. So breaking load is recorded, and then after testing, because the fibers edges are cut after gripping, so after testing, the fiber specimens, broken fiber, the broken fibers are taken out. So from the left jaw and right jaw. So from left jaw, the broken fibers will be, after taking out, this will be the from left jaw, and from right jaw, this will be the total mass of fibers which were gripped, which were taken part during the testing. So from this relationship, we can calculate the tenacity or tensile strength of the fiber bundle. So the stelometer is the method. The stelometer term came from strength ST elongation. ST is strength, ST is strength, and elongation, ELO. So you join together. So stelometer and this works on pendulum lever principle, that we will discuss separately. Another method is Presley fiber strength tester, and which works on pivoted beam balance principle. Okay, and also in high volume instrument tester, so HVI, we also measure the bundle strength. So in discussing the length measurement, what we have discussed, the fibrosampler, this is a fibrosampler, is prepared to measure the fiber length. So their fibro sampler is used to measure the fiber length. By light scanning, we get the fibrogram. So fibrogram we get after testing the length. The same the sample is used to test the strength, and that is also in the form of bundle strength. Now we will discuss the terminologies. There are different tensile test related terminologies. So we must understand, and we also must understand the difference between these terms and their interrelationship also. Breaking load or breaking strength. So what is breaking load? The load required to break the material. So in a specimen, if we see the load elongation curve, this is the load elongation curve, and at this point the material breaks. That means the load. So here in x-axis it's a elongation, and y-axis it's a load. The load required to break the material, it's called breaking load. Stress. So stress is expressed for any uniform engineering material, any uniform material where we can measure the cross section correctly. The stress is force per unit cross sectional area. So suppose this is the load, in P is the stress load required to break this material in B, and the cross sectional area of this material is A. So stress will be in B by A. That is, stress means breaking stress will be this. But for textile material, it's difficult to measure the cross sectional area. That we have already discussed. The reasons are the fibers are not circular in cross section, and during yarn manufacturing we impart twist which makes the cross section non-circular. So what we do, so as the fiber cross section are fiber, yarn, even fabric are irregular in nature, exact cross sectional area of fiber, yarn and fabric is very difficult to measure. So we have to see the alternate way to express the stress. Here we express the stress in terms of the specific stress, that is stress load per unit linear density. So in case of textile material, we don't get the cross sectional area. So instead we have seen we measure the linear density, mass per unit length, and we express for yarn, we know that we express in terms of text. So suppose one yarn is breaking at the load of say 20 Newton or 27, sorry, yarn is breaking at say 200 centinewton load, and the linear density of the yarn is say 10 tex. 10 tex is the linear density. So the breaking stress is calculated as 200 divided by 10, 20 centinewton by per tex. So to differentiate with normal stress, where load per cross sectional area is used, here we express this in centinewton per tex, and it's based on the mass per unit length, that is linear density. We can call it this stress as also mass stress, and this linear density of the yarn or any material is the linear density at the initial stage before any elongation. As we elongate, the text value will change, it will decrease, because that it's a mass per unit length. So length is for same mass, we are changing the length. So suppose it is a 100% elongation. For example, elongation is 100%. So the after elongation, the text value will become half, say 5 text. Say typically 100% is too high, but for our example, let us assume, so it is 5 text. So when the material is breaking, at the breaking point, the linear density is 5 text, not the 10 text, but still we use the 10 text for calculating the stress. So always one should remember the load per unit linear density. The unit linear density is the starting linear density, not after the elongation. Now this is typical load elongation curve that we have already discussed. So this is the breaking point, and from breaking point we can calculate the breaking load and breaking elongation. So the elongation at which the material breaks, that is breaking elongation. And initially there will be straight line for some time. After that there will be a deflection from this straight line towards the elongation axis, and this point is known as yield point. Apart from load elongation curve, there is another curve which is called stress strain. So stress strain curve means we originate the stress strain behavior from the load elongation behavior. Now let us try to draw the load elongation curve. This is the load elongation curve. Load elongation curve. This is say centinewton and elongation it's millimeter. This is load and this is millimeter elongation. Okay, and from load elongation curve we can convert this load elongation curve to the stress strain curve. This is stress, x-axis is strain. Now to convert the load elongation curve to stress strain curve, we need few parameters, because for any tensile testing it measures the load and elongation, and we can convert it to stress strain curve by knowing the initial initial linear density. So initial linear density say T initial. Okay. And another parameter we need, the gauge length. Gauge length, as we have discussed, the length between the two jaws before testing starts. That is gauge length. So these two parameters are required to convert the load elongation to stress strain. Now let us see. Stress. So suppose this point we want to measure the stress. So we know the load L1. Sorry, this is the so this is here strength load S1, and when we divide this to initial linear density, so it will become ST, stress equal to S1 by T initial. So that we are plotting this. Similarly, we for another point say S2, it will become S2 here, which is this will be ST1. So ST2 will be S2 by T initial. So in this way we plot, but at the same time what we have to plot also strain. So we know the elongation E1 and E1 is the elongation at that point where we get the load S1. So at this point the strain will be E1 by L. So E1 by L is the strain at this point. E2 by L is the strain. So by the initial gauge length. So strain is the ratio of elongation in millimeter by the initial gauge length L. Similarly, when we apply stress, the material get straightened. So from earlier example, initially say 10 millimeter was there, it has become 20 millimeter. But we calculate based on the initial gauge length. So this is the point. In this way we convert the load elongation to the stress strain. Let us see the animation here. So first let us draw the load elongation. This is the load elongation curve. And the point where the curve bends, it's a yield point. So breaking point is identified at the point where it is breaking. From there we can calculate the breaking load and breaking elongation. Now stress strain, if you see, we can plot as we have discussed earlier. So load is divided by the linear density. Here in text, load is given in gram force. So breaking point, at the breaking point, the stress at the breaking point is known as the tenacity, breaking stress or the tenacity of the material. So in place of stress, where the cross section is very uniform, here we use the specific stress or mass stress that we have discussed. So this is the breaking point. In stress strain curve we call it as tenacity.
Stress or specific stress, because it's a load per unit linear density. So whether, that's why actually the mass component is there, so we call it as mass stress. Okay. So, as the linear density is a mass component, so we call it as a mass stress. Okay. And this is the stress strain behavior of the any yarn or any fibrous material or any material. So, this is the yield point. So, where there is a sudden change in the inclination, it is beyond the Hooke's region. So, from this yield point we can identify the yield stress and yield strain. So, let us draw another stress strain curve where we can see here. So, we will discuss here two types of structure. So, in the x axis is strain and y axis is stress. So, this is one breaking pattern of this here, where the breaking pattern is such that the breakage does not take place at the value. Okay. Unlike earlier one. So, this is the point where the peak point and the point here is the breakage point. The breakage point is lower than the peak value. Okay. So, where fiber to fiber slippage takes place in textile material. So, this type of phenomena happens. Okay. And after reaching the peak value where the fiber to fiber slippage takes place, still there is no disintegration. So, slippage takes place. So, it ultimately disintegrates at the point which is lower than peak point. So, what will be the tenacity here? So, we have got two different types of stress. One is the peak value, and at the point S2 the material breaks. So, here if you see from this diagram, the tenacity we can define from the S1. So, here the tenacity is the actually the stress at the highest point or peak point, not at the point where it breaks like S2. So, S2 is not the tenacity, here S1 is the tenacity where the maximum stress possible in any material. So, mass stress in case of textile material is the linear density is used in case of instead of cross section. Okay. And here you can see it also allows the linear, for different linear density we can compare the specific stress. Okay. If we want to compare the tenacity of two different types of yarn, say one yarn is coarser yarn 10 Ne, another finer yarn which is 50 Ne. So, if we get the stress strain behavior, we can simply compare the tenacity of the materials. Now, let us consider the two materials. One is say 10 tex yarn, which is having the breaking load is 100 centinewton. Another yarn which is coarser one, where the breaking load is say 140 centinewton. So, apparently it looks that yarn 20 tex yarn is 140 centinewton. So, can we tell that 20 tex yarn is stronger than 10 tex yarn? So, if we want to compare, so in that case we have to get the tenacity value. So, let us yarn 1 is 10 tex, yarn 2 is 20 tex. For yarn 1, the tenacity we will get is 100 by 10, 100 centinewton by 10 tex. So, 10 centinewton per tex. For yarn 2, the tenacity will be 140 centinewton by 20 tex. So, 7 centinewton per takes, although the yarn 2 with 20 ticks has got higher breaking load, but if we compare the tenacity, it is lower than the yarn 1, which is 7 cm per ticks. So, to compare, we have to use the linear density. Okay. So, therefore, the tenacity is the force per linear density of the material at initial stage. So, tenacity we can define the specific stress at break, or specific stress corresponds to maximum force. So, that because whichever is higher. So, a specific stress at break is not always true, but we can always consider that it is corresponding to the maximum force available in the stress strain or observed at the stress strain curve. So, we have already discussed the specific stress is the tenacity, or tenacity is the value which is the maximum point at the stress strain behavior. Here you can see for yarn with a green color, it was higher than the blue color. Okay. So, thank you.